We said in the last video that the derivative will kind of, quote, distribute over addition and subtraction. However, that is not the case. The derivative will not distribute over multiplication and division. This is a little bit more difficult for us to work with. We are, for right now, sort of going to have to find workarounds for dealing with multiplication and division because we don't really know how to deal with those quite yet. So in these next few examples, we're just going to look at, well, how can we kind of work our way around so that we actually don't have multiplication and division, because right now we don't know how to deal with that. So here, f of x equals 12x cubed minus 8x squared plus 12x all over 4x. Now I can't just take the derivative of the numerator and take the derivative of the denominator, and I'll show you why that is in just a second here. Right now, I want to think about, how can I rewrite this expression? How can I rewrite f of x so that it doesn't have any sort of division happening? I think division's a little bit trickier to deal with, and you wouldn't normally write it this way, but I'm really going to peel this off into three separate fractions. I'm going to say, well, this is 12x cubed over 4x. This is negative 8x squared over 4x. And this is 12x over 4x. I'm sort of going to pull this apart. So 12x cubed all over 4x minus 8x squared over 4x plus 12x over 4x. Normally, most of the time, we would kind of start over here on this side and work our way towards the left-hand side. Once we find that common denominator, we say, okay, we want to write that as a single fraction. Here's an example, though, where I would rather have three separate fractions. And the reason I'd rather have that is because now I can simplify each one of these terms. I can do a little bit of division and cancel some terms. So here, 12x cubed over 4x, I should have, what, 3x squared, minus 8x squared over 4x, that should be minus 2x, plus 12x over 4x, I should have plus 3. Now notice, we haven't actually used the power rule. So we haven't actually taken the derivative yet. Notice, f of x is equal to this, is equal to this, is equal to this. This is still f of x. I have not yet taken the derivative, which means I still need to do that. So let me do that real quick here. I'm going to take the derivative of this function right here. So f prime of x, when I go to take the derivative, should look like 6x minus 2. Here is my derivative. So I know that that's my derivative. Let me show you really quickly why we can't just take the derivative of the numerator and the denominator. So let me do that. Let me make some space right here. So if I was working with f of x equals, I'm going to rewrite the expression 12x cubed minus 8x squared plus 12x all over 4x. If the derivative worked the way I think a lot of us would like, I would just say, well, let's just take the derivative of the numerator and then take the derivative of the denominator, and then we'll divide the two. That's kind of what you would almost do intuitively. Well, the derivative of the numerator, let's see, I should have 36x squared minus 16x plus 12 divided by 4. If I divide each one of those terms by 4, let's see, 36, I would have 9x squared minus 4x plus 3. This is a really big problem because I've essentially found the derivative two different ways and ended up with two different answers. The first way, I said I kind of took the long way around, but I said, you know what, I know that this is the derivative, because I know that this f of x, this original expression, is equal to this, and I know how to deal with that polynomial. I know how to deal with 3x squared minus 2x plus 3. This guy right here, we tried to take a shortcut that we weren't quite sure worked out. And this is a problem because this this isn't equal, right? 9x squared minus 4x plus 3 is different than 6x minus 2, which means that they both can't be the derivative. The derivative has its properties called unique, which means for each function there's exactly one derivative. So that means that this shortcut that we tried to take won't work. It's not going to work for us. So right now we have to kind of just find ways around this division so that we can rewrite it so that it doesn't involve division. Then we can use our power rule. Part B, very similar idea, only now I have multiplication. I have 3x plus 1 times 4x squared minus 9. I would like to multiply these together. Whoops. Before I actually go to take the derivative, I'm just going to go ahead and FOIL this out. So 3x times 4x squared, I'll have 12x to the third power. 3x times 9, let's see, minus 27x. 1 times 4x squared, I'll have plus 4x squared minus 9. So this is still, notice this is still y. I haven't actually used my power rule. But I've rewritten it in a way so that now I don't have any multiplication and division. All I have is addition and subtraction. So I can just use my power rule like I have been. Let's see, I should have 36x squared minus 27 plus 8x. It's not in standard form, but I don't really care. And then, of course, derivative of negative 9, that's just 0. So here is my derivative. Again, if you want to see why this doesn't work out, if we start with y equals 3x plus 1 times 4x squared minus 9, if I try to take the derivative of each of those factors separately, derivative of 3x plus 1, that would be 3. Derivative of 4x squared minus 9, that would be 8x. 3 times 8x, I have 24x. That's a whole lot different than what we ended up with for our actual derivative. So again, here, for this guy, we tried to take a shortcut. That shortcut does not work. So we're going to have to find ways around multiplication and division. Most of the time, it's just simplifying the expression as much as we possibly can. Now, there will be times when we simply can't simplify the expression. If I was working with, say, just as an aside, if I was working with, say, 4x e to the x, I can't really simplify this. I have 4x times e to the x. There's really not a great way for me to simplify this. So at some point, we are going to have to confront this problem of how do we deal with multiplication and division, or something like 4x divided by e to the x. How do we deal with that? Well, that's a problem for future class. We don't want to worry about that right now. Lastly, h of t, here I have, not lastly, second to lastly, I suppose. I have h of t equals square root of t times square root of t minus t to the 3/2 power. So most of us, I think, would probably guess, well, okay, I'm going to take that square root of t and distribute that, and you'd be absolutely right. Square root of t times square root of t, that's going to get rid of my square root, that's just t. But this part right here might be a little bit tricky if we're not familiar with our exponent rules. Square root of t, really I have square root of t times t to the 3/2. And here there's an exponent rule that will come in handy. It's that this guy right here, square root of t, is actually t raised to the 1/2 power. It's going to be a really important property for us later on. So I have t to the 1/2 times t to the 3/2. When I'm multiplying two like variables, I add their powers. I'll have t to the 4/2, which is just t squared. So I have t minus t squared. Again, I have not taken the derivative. All I did was simplify this expression, which means I still need to use my power rule. So h prime of t is equal to 1 minus 2t. Here is my derivative. Last example for this particular type of problem, I have y equals 2e to the x plus e to the x, all divided by e to the x. again, we're going to pull the same exact trick that we did earlier. I'm going to pull it apart into two separate fractions and say, well, this is 2e to the x divided by e to the x plus e to the x divided by e to the x. So really what this says, and this is kind of a silly way to write it now that I look at it, because this really says 2 plus 1 is equal to 3. But this is still y. I haven't actually taken the derivative. So this is still y, which means when I go to take the derivative of 3, it's just 0, because 3 is a constant. So, hey, there we go. Another way, I suppose, actually, now that I look at it, we could have simplified this. Another way we could have done that is we could have said this is y equals 3e to the x divided by e to the x, then cancel these two to just be left with 3. Doesn't really matter how you approach it. Either way, we get the same solution. Last thing that I want to mention in this section is higher order derivatives. So if we're working with a differentiable function, if we're working with y equals f of x is differentiable, we have the second derivative of f is denoted either d squared y over dx squared, or sometimes more simply, more often, we'll probably just say f double prime of x. What does the second derivative look like? The second derivative is just the derivative of the first derivative. So I take the derivative, and then I take the derivative again. I just take the derivative twice, sort of almost exactly what you would expect. The third derivative would be d cubed y over dx cubed. More commonly, we'll write that as f triple prime. Well, that's just the derivative of the second derivative. So I will take the derivative, and I'll take the derivative again, and I'll take the derivative again. And I can continue that as many times as I want. The nth derivative, if I ever asked for, say, the 100th derivative or something, this is d to the nth power y over dx to the nth power. Whoops, that's my fault. Dx to the nth power there. And the way we denote that after the third derivative is we start to use this notation here. We'll say f, the nth derivative of f. There's really not a great way to talk about that, so I would say the nth derivative of f. I don't want to say f to the nth power because that actually means something entirely different. So that just means, hey, you take the derivative of your function n times. So if I want the fifth derivative, I got to take the derivative 5 times. If I want the 100th derivative, I'd have to take the derivative 100 times. So that would be kind of annoying to have to do unless you knew some tricks or something like that. This last example here, I'm going to find the first derivative, the second derivative, and the third derivative for this function. F of x equals 3x cubed minus 5x squared plus 10x minus 11e to the x. So first derivative, I can just use my power rule. Well, mostly use my power rule. 3x cubed, well, that's going to be 9x squared when I take its derivative. Negative 5x squared, that's going to be minus 10x. Derivative of 10x, that's going to be plus 10. This guy right here we might have a little bit of difficulty with. It's just a little bit different. But remember, this is just a constant multiple here, so minus 11 times the derivative of e to the x. What's the derivative of e to the x? We said earlier that derivative is just e to the x. So the derivative of negative 11e to the x is negative 11e to the x. If I were to take the second derivative now, I'm just taking the derivative of this function right here. I'm taking the derivative of the first derivative. Actually, let me just do that in a different color. So f double prime of x. All right, derivative of 9x squared, that'll be 18x. Derivative of negative 10x, that'll be minus 10. Derivative of 10, that's a constant, so I know that's going to be 0. That term drops off. Derivative of negative 11e to the x, well, that's the same as the derivative of negative 11e to the x, right? That the derivative of e to the x is simply e to the x, so minus 11e to the x. There's my second derivative. If I wanted my third derivative, f triple prime of x, and okay, let's take the derivative again here. Derivative of 18x, that's just going to be 18. Derivative of negative 10, that's a constant, so that's just 0. And derivative of negative 11 e to the x, well, once again, it's a constant multiple of negative 11 times the derivative of e to the x, which we said that was just e to the x, so minus 11 e to the x. And just for funsies, let's look at the fourth derivative. The fourth derivative of x, derivative of 18, derivative of 18, that's a constant, so that's going to be 0, minus derivative of negative 11 e to the x. Hopefully we're sensing a pattern here. We'll have negative 11 e to the x. What about the fifth derivative? Well, this is just 0. We don't really even care about that. Derivative of negative 11 e to the x is just negative 11 e to the x. We could just continue this all day. So if I wanted to say the 100th derivative of this function, it would still just be negative 11 e to the x. So can we always assume that this is going to be true, that this is always going to be happening? No, we can't. But sometimes if you take the derivative enough times, you can start to identify a pattern, and you will be able to talk about higher order derivatives if you can identify the pattern. For the most part in our class, we really care about the first derivative and the second derivative. These are what we're going to be using most in Calculus 1. However, you may use the third and the fourth derivatives in higher levels of calculus. So if you plan on taking Calculus 2 or Calculus 3, you will probably see the third and fourth derivatives make a comeback. So that's all I've got for this section. If you have questions, please feel free to email me. Otherwise, good luck on the homework.